In this video, we're going to learn how to solve applied problems involving right triangles. So two definitions I want to get out the way right away are angles of elevation and angles of depression. Now the best way to understand what these are is imagine you are at a point like your eye, your vision, and if you're looking upwards at an object, if this is the horizontal from your eyes with the ground, that angle upwards is what we call an angle of elevation. And if you're ever looking at an object below that horizontal, like below you, that's an angle of depression when it goes downwards. And again, that little dotted line is always like kind of that line of sight, and you always have a horizontal. So that line of sight is always in relation to a horizontal of some kind. Now, here we have a laser beam. This is the first example. A laser beam is to be directed through a small hole in the center of a circle that is of radius 10 feet. So the circle has a radius of 10 feet. And the origin of the beam is 35 feet from the circle. So this laser is 35 feet from the circle. At what angle of elevation should the beam be aimed to ensure that it goes through the hole? So again, you'll see here, this is the horizontal on the ground. It's angling upwards to create the angle of elevation, and we're looking for that angle. So we're looking, how do we direct this laser to point right through the hole? And since it's a very small hole, you have to be very accurate. So it may not be up to guessing. We're going to calculate it. So here I do have a right triangle forming. If I drop a line straight from the hole in the circle, straight down, you can see a right triangle form. Now this distance from the center of the circle to the bottom of it is 10. Since we know that the radius of the circle is 10 feet, that distance must be 10 feet. And this bottom distance is the distance from the laser to the circle, which we know is 35. So we have a right triangle. We know two of the sides, and we're looking for a particular angle. So from this angle, 10 would be the opposite side, and 35 would be the adjacent. So opposite over adjacent makes me think of tangents. So I'm going to solve for this angle using tangents is equal to the opposite side, which is 10, over the adjacent side, which is 35. Now we're going to solve this equation to get that angle by using an inverse trig function. And we'll get that theta is equal to tangent inverse of 10 over 35. You could simplify that fraction on the inside, but we still will need to plug this into the calculator. This gives us 2/7, but it still doesn't tell us what the angle is. So I will take my calculator. I'll plug in tangent inverse of 2 divided by 7, and it'll give me 15.945 degrees. That's the angle you need to angle it up to get it through that hole. Now let's look at a little bit more of an involved problem. So say we have a blimp suspended in the air at a height of 500 feet, lies directly over a line from Soldier Field, which is a stadium, to the Adler Planetarium on Lake Michigan. So this is the line between them, and the blimp is directly above it. So 500 feet is a distance from the blimp to the ground. So I'm going to write in 500 feet is that distance. Now, if the angle of depression from the blimp to the stadium is 32, so again, angle of depression always comes off of a horizontal. So you can't make the angle over here with this vertical line because you can't use a vertical. So if I make a parallel line with the ground, which is usually a horizontal. Here's my horizontal, and I'm having my angle of depression be 32 degrees. So that's where that angle would be, the angle of depression. And then from the blimp to the planetarium, the angle of depression is 23. So over here is 23 degrees. Now find the distance between Soldier Field and the Adler Planetarium. So I'm looking for this distance between the two. Now there's no guarantee that this is a right angle, so I can't assume that. But what I can assume is that height from the blimp straight to the ground, that should make a right angle with the ground because that would be the shortest distance. So I have two right triangles I can use. And I'm going to be looking for this length on the left, which I'll just call x, and this length on the right, which I'll call y. They're part of those triangles. Now, these angles aren't a part of this triangle, but since the ground and this horizontal are parallel, I can use those alternate interior angles to find that 32 degrees is equivalent or congruent to the angle, the base angle on this right triangle by Soldier Field. So this angle over here would also be 32 degrees. Now you can also make the argument that up here, this vertical goes up to that horizontal, which makes a right angle, and you can use the complementary angle. But this one feels a little more accurate, or a little more like easy to follow. So over here, again, the horizontal up here should be parallel to the horizontal down here, alternate interior angles. This should be 23 degrees as well. So now I have two right triangles that share a side, and I'm going to be looking for these missing sides. So to help myself, I'm going to redraw these triangles. And solve for that missing side. All right, so now I have an angle, and I have the opposite and the adjacent side. So what I can write is the tangent of 32 degrees is equal to the opposite side, 500, over x. So if I multiply each side by x, I get x times tangent of 32 degrees is equal to 500, and then x is going to be equal to 500 divided by the tangent of 32 degrees, which I'll calculate in my calculator in just a minute. And I can also do a very similar practice over here because I also have the opposite and the adjacent side to the 23 degrees. So I can say that tangent of 23 degrees is equal to the opposite side, which is 500, over y, and solve it in a very similar way. Multiply by y. And then divide by tangent of 23. So y will equal 500 over the tangent of 23 degrees. So that distance between these two is x plus y, which would be 500 over the tangent of 32 degrees plus 500 over the tangent of 23 degrees. Which when I look at this, I don't really see that distance, just gazing at it. So I'm actually going to plug that into my calculator to actually see what that distance would be. So I have 500 divided by the tangent of 32 degrees. So that's one fraction, plus 500 divided by the tangent of 23 degrees. Hit enter, I get a distance of 1,978 feet. So 1,978.093 feet. And that is how you solve applied problems involving right triangles.